Okay, we are registering now. Okay, so can you see the slides from remote?
Yes.
Okay. So let's continue from the point we left yesterday. So yesterday we started introducing transformations with the idea that the so-called symmetry transformations are transformations that leave the Lagrangian unchanged, as we will see today. Okay, so will not affect the physics. And there are several types of transformations. So let me just remind you that transformation can be split into main families: the discrete transformations, such as parity, charge conjugation, etc., that we will be studying next in the course, and the continuous transformation, which are further divided into space-time transformation, which include translations, rotations, Lorentz transformation, etc., and internal transformation, which instead act on the internal quantum numbers. And these are further divided into two subfamilies: the global transformation, where the parameter of the transformation is global, so it does not depend on the space-time coordinate. An example of these are the SU2 isospin, SU3 flavor, that we will study at the proper time, of course, and the local transformation, which are more general, and now the parameter or the parameters of the transformation depend on the space-time coordinate, as we will see today. Okay, so let's continue in this direction. But let me first just summarize in one slide what is a group, okay, because this is relevant for transformation, because we already mentioned yesterday a group of transformations, if you remember. So in general, a finite or infinite set of objects or transformations, A, B, C, D, whatever, is said to form a group G if there is an operation that we call product, and we represent with this symbol here, between any of its elements, such that, so the product C A times B of two elements, A and B of a group, is also an element of the group. There is one and only one identity element, I, such that the product of any element A by the identity element I returns the element itself. Okay. Each element has an inverse, and the product of an element by its inverse element returns the identity element. The associative property holds, so A times B times C is equal to A times B times C, or A times B times C. And if the commutative property of the product holds for any two elements of the group, then the group is called abelian. Otherwise, it is called not abelian, non-abelian. Okay. So this is general for any kind of group, okay, meant as a mathematical concept. Now we will use this concept, of course, for our case, so for the group of transformations in particular. So let's start with rotations. Rotations are an example of continuous space-time transformation. Each rotation is labeled by a set of three continuous parameters, alpha 1, alpha 2, alpha 3, that corresponds to the Euler angles, as you know, which can be regarded as the component of a vector, alpha vector, which is directed along the rotation axis. Now, the set of rotation of a system form a group. Okay, each rotation is an element of the group. So two successive rotations, R2 times R1, these R1 followed by R2, are equivalent to a single rotation, here to another element of the group itself. In particular, every finite rotation can be expressed as the product of a succession of infinitesimal rotations. Okay, and this holds in general for any continuous transformation, so not only for rotation but also for translation, etc. There is an identity element, which is just no rotation. Every rotation has its inverse, so the rotation in the opposite direction, trivially. And the product of the rotation is, in general, not commutative in space. Okay. Now, having said this, by definition, the dynamics of the physical system is unchanged by a symmetry operation. So by symmetry operation, I mean any kind of transformation that leave the physical system unchanged, unaffected. Okay, in this sense, it is a symmetry transformation or operation. For instance, Since we don't want an experimental result to depend on the specific orientation of the system under study, of course, rotations must form a symmetry group for any physical system. Okay, this means that the system is unaffected by the rotation. The physical results is the physics is unchanged. Now let's try to introduce some formalism. So under a certain rotation R, the state of the system transforms from psi to psi prime, which you can get from the region of psi after applying some operator U, which encodes the transformation. So for instance, the rotation in this case. If the system is symmetric under this transformation, then of course the operator U must commute with the Hamiltonian of the system. Okay? And the physics must be affected. So for instance, the probability that the state psi evolves into the state phi must be unchanged by the transformation. And in order for this to happen, this is only possible if you follow now this chain of equalities. This is only possible, just look at the last passages, if daga U is equal to the identity matrix, okay? And so this implies that the U operator must be a unitary operator, okay? So if U is unitary operator, then indeed the physics is unaffected because your probability for psi prime to phi prime is equal to the probability for psi to phi, okay? Now, let's consider an infinitesimal rotation, so a rotation by an infinitesimal angle epsilon about the z-axis, for instance. So one can make a power expansion of this rotation, okay? And at the first order, in this small parameter epsilon, this operator corresponding to an infinitesimal rotation is written in this way: 1 minus I epsilon jz. Of course, one can have here higher order terms in epsilon, okay? Squared, cube, etc., which we neglect for the moment. Now, if you remember, by rotation a continuous transformation, it is always possible to obtain a finite rotation, so a rotation by a finite angle, as an infinite succession of infinitesimal rotations, okay? So if you want now to calculate our rotation operator by a finite angle theta, okay, this is equivalent to essentially apply infinite times the transformation for an infinitesimal angle epsilon, okay? So we go in the limit where n goes to infinity. Now we write the full expression of our, the approximate expression of our elementary rotation. We can express epsilon, which is the infinitesimal angle, as the finite angle divided by n, which is the number of steps, okay? And this limit is a non-limit from mathematical analysis, and it is equal to e to the minus I theta jz, okay? So overall, we found that this operator, the rotation corresponding to a finite angle, we can express as e to the minus I theta jz. So let's look into this more in detail. So the theta that appears here is called the parameter of the transformation, and the object, okay, beside theta, so jz in this case, is called the generator of the transformation. Okay. In this case, since we are dealing about rotation with respect to the z-axis, the generator corresponds to the third component of the angular momentum, as you know already from quantum mechanics. Okay, but this is just an example. Okay. Now, if the physical system is symmetric under rotation around the z-axis, then of course the third component of the angular momentum must commute with the Hamiltonian of the system. And so the third component of angular momentum is conserved, is a conserved quantity. And if you remember, yesterday we speak about the Noether theorem. This is just what we meant. So a symmetry of the system always corresponds to a conservation law. The system is symmetric under rotation around the z-axis, then the third component of angular momentum is conserved and commutes with Hamiltonian. Okay. Now, a unitary group, this is in general, okay, so we are back to mathematics now, abstract mathematics, if you like. A unitary group, UN, is a group of unitary complex n by n square matrices. And the simplest element of this group, of course, is U1, which has just one free parameter, and so just one generator. So a U1 transformation is also called a phase transformation. It is of the type e to I alpha and some operator, capital A, okay? Where alpha is a real number, which is indeed the parameter of the transformation, and A is a Hermitian operator in general. Now, one can consider the most relevant cases, and indeed the most relevant case is when the operator I is just the identity matrix. Okay, so our phase transformation reduced to simply e to I alpha. Or it could be an operator associated to a single measurable quantity, like for instance the electric charge. So in the latter case, the Noether theorem ensures that the invariance of the Hamiltonian with respect to such transformation entails the conservation of the corresponding measurable quantity. So for instance, the electric charge. Now, unitary groups, as well as special unitary groups that will be studied next in the course, SU, of transformations. So now let's get back to transformations of a generic rank, could be 1, 2, 3, whatever, are extremely important for our scope because they play a central role in particle physics, since they are the basis of the theories of fundamental interactions, as we will see. Okay. So, yesterday we introduced the Lagrangian density for a scalar particle, if you remember, and for a free fermion. And once you introduce the Lagrangian density into the Euler-Lagrangian equation, you get, as a result, the equation of motion. So the Klein-Gordon equation in the first case, and the Dirac equation, or the adjoint Dirac equation in the second case. Okay. So if you remember, this was the expression. This is the expression of the Lagrangian density for a free fermion. Okay, we have a kinetic term here, the first part here, and then we have a mass term. There is no interaction at this level. Okay, we are considering only free particles, free fields, to be more precise. Now, it is easy to show that this Lagrangian density is symmetric under a global phase transformation, so the one that we just mentioned before, E I alpha. Okay, so under this transformation, our field, which is psi x mu, transforms into psi prime x mu, which you obtain by applying this unitary operator over your field. Okay, which we can now make explicit as E I alpha psi mu. Okay, so let's now show on the blackboard that indeed this Lagrangian for a free fermion is symmetric for global phase transformation of the kind E I alpha. Okay. Let me write down the Lagrangian density, I, bar, mu, then psi minus n, psi bar, psi. So let's apply now this phase transformation. So our state psi goes into a psi prime, which is equal to E to I alpha psi. Vedete bene da casa, ragazzi? Hello?
Sì, prof.
Okay. Now for the adjoint spinor, psi goes to psi bar prime, okay, which is psi bar e to the minus I alpha. We put that here the complex conjugate, of course. Now, what about the derivative? The mu psi goes into the mu psi prime, so the mu of e to I alpha psi, that is e to I alpha the mu psi. All right. Now let me, before going on, let me point out that the derivative of the field transforms in exactly the same way as the field itself. Okay, you just have the exponential on top of it. And this is a relevant argument as we will see next today. So for global transformation, the derivative transforms exactly in the same way as the field. Okay? Okay, now let's introduce everything here into our transformed Lagrangian density. So the L prime. The L prime is I, psi bar prime, gamma mu, d mu, psi prime, minus m, psi prime, bar, psi prime. And let's just substitute our ingredients. So we have I, psi bar prime is here, so it is psi bar e to the minus I alpha. Then we have gamma mu. Then we have the derivative of psi prime, that is this guy here. So e to I alpha, d mu psi. And we are here. And then we have the mass term. So minus m e to minus I alpha psi bar e to I alpha psi. Let's now write this in a more convenient way. So we have I, psi bar, gamma mu, e to the minus I alpha times e to the I alpha psi, the mu psi, minus m e to the minus I alpha e to I alpha psi bar psi. Okay. Now, this is trivially equal to 1. This is also trivially equal to 1. So we obtain just I psi bar gamma mu d mu psi minus m psi bar psi, or that means the untransformed Lagrangian. Okay. So at the end, the transformed Lagrangian and the untransformed Lagrangian are equal. This means that this phase transformation here is a symmetry transformation for our physical system, because it leaves the Lagrangian unaffected. Allora, questo è morto già. C'è un po' nero, mi sa che è anche peggio. Ok? Okay, let's continue on the slide. So, the family of phase transformation or a phase global transformation, where the parameter alpha of the transformation does not depend on the space-time coordinate, it's just a real number, form a unitary abelian group known as the U1 group. Abelian means that it is a commutative. Now, based on the Noether's theorem, a symmetry under a global U1 group transformation, the one that we just derived on the blackboard, implies, of course, the existence of some conserved quantity, in particular a conserved current. So to see this, let's consider again the Dirac Lagrangian for a free fermion field, okay? And we now impose that it is invariant under this phase transformation. Actually, let's take an infinitesimal phase transformation, okay? And we'll see what we get by imposing that now the Lagrangian is unaffected, is symmetric. Questo mi serve tutto. Ah no, ok, no, let's do this because it is now an infinitesimal transformation. So our U alpha is now of the form 1 minus I alpha. So let's start again. Our transformed field is going to be U psi, it is 1 minus I alpha psi. About the adjoint, this is, in this case, when you have the adjoint, usually the operator acts on the left side. Okay, so this is psi prime, and then we have the complex conjugate, so 1 plus I alpha. Now let's take the variation, the difference, delta C as psi minus psi prime. So it is psi minus 1 minus I alpha psi, that is I alpha psi. And also for the adjoint spinor, so delta psi prime, sorry, this is psi bar minus psi bar prime, that is psi bar minus psi prime, 1 plus I alpha. And so we have a minus sign here, this is minus I alpha psi bar. Now let's work out the derivatives. So delta of the mu psi, this is the mu psi minus the mu psi prime, that is the mu psi minus the mu 1 minus the alpha psi, that is I alpha the mu psi, and similarly the mu psi bar is equal to the mu psi bar minus the mu psi bar prime, that is the mu psi bar minus the mu. Here we have the bar 1 plus I alpha, and it is minus I alpha the mu psi bar.
Sorry, may I ask a question?
Yes, please.
Why is it lower mu on the derivation? I'm just a bit confused with the notation.
Okay, here we are, I think, consistent everywhere. Okay, the important thing is to be consistent everywhere. So if you use it lower, it has to be lower everywhere. If you use the upper, it should be up everywhere. Right?
Because it's symmetrical as well with the years.
Yes, the important thing is not to mix upper and lower indices. So if I'm using lower everywhere, that's fine. Okay, if you use upper everywhere, it's also fine.
But we need the upper one in the Lagrangian.
Yeah, okay, then you can, okay. Trivially, you can invert, you can repeat it with the upper if you like, okay, it's just the same. I'm not a theoretician, so I'm less strict with these kind of formalities. Okay.
Sorry, I'm still confused.
Thank you for your question. Okay, let's now write down the variation of the Lagrangian. So can I clear the board? Are you all done with this? So delta L. So let's take now the full differential of our Lagrangian density. So this is in general the L in the psi plus the L in the psi bar del psi bar plus the head in the mu psi the mu psi plus the mu psi bar delta the mu psi bar. So it's the total differential of our Lagrangian density. And let's substitute here the ingredient that we derived before. So this is dl in the psi, and then this is just I alpha psi plus minus I alpha L in the psi bar. Okay. Now we have plus L in the mu psi times I alpha the mu psi, and then the last term is minus I alpha the mu psi bar L in the mu psi bar. Okay, now we read some algebra, some very boring algebra, which I will not do on the blackboard, but you find in the next slide. Okay. And so let me go to the result of this. I alpha the mu dl over d in the mu psi minus psi bar dl in the mu psi bar. So we arrive to this point. Okay, now we have to compute these derivatives here by taking into account the expression of the Lagrangian density, as we did yesterday, essentially. So for the Lagrangian equation, so dl over the mu psi is the mu psi of our Lagrangian density, I psi bar mu the mu psi minus m psi bar psi. The derivative is I psi bar gamma mu, and and the other term is dl in the mu psi bar now. This here. So it is the mu psi bar of our Lagrangian, I psi bar the mu psi minus m psi bar. And here we don't have any derivative on the adjoint spinor. So this is just 0. Okay, so we don't have this guy here. So let's now continue from here. Let's substitute. So what we have is I alpha the mu, is this term here. Then we substitute what we found from our derivative, I psi bar gamma mu, and then just psi from here. Okay. This we can write in a slightly more convenient way. So I have plus times I need to remember minus sign. So this minus, they move. We have alpha, then we have psi bar, then we have gamma mu, then we have psi. And now we impose that this is 0. Or in other words, we require that our Lagrangian is symmetric under this transformation. So there is no variation between the transformed and untransformed. Okay. And so, since now this derivative we impose is equal to 0, then as a consequence, let me go here. Obviously, this quantity is conserved. Okay. So, but what is this quantity? It's nothing else than our vector current. So it's just alpha, psi bar, gamma mu, psi. And this is a constant. This is a vector current.
I don't understand why we have that E alpha, the nu in psi value gamma mu is equal to minus the nu.
I times I gives you minus sign.
We have the psi bar gamma mu. Why there is a even the psi?
This comes from the derivative here, right? You want this term here, you mean?
Okay.
This comes from the derivative here, so this is included in this term here. Okay, so what we did here, we forced our Lagrangian density to be symmetric under this infinitesimal transformation, and as a result of the Unitary theorem, we got a conservation rule. This for current must be conserved, must be constant. So let's comment more on this on the slide. Okay, so this is the slide with the algebra that I skipped, but you have all the details here for your happiness. Now, so requiring that the Lagrangian is symmetric implies the conservation of these four current. Now assume that psi represents the electron field. So one can redefine the arbitrary parameter alpha in terms of the electron charge. So if you put minus c instead of alpha, what you get here is essentially the electromagnetic force-current, which is conserved. And this is again, we get back again once more to the continuity equation that we derived from the Dirac equation, if you remember, okay? Where the conservation of force-current implies essentially that all these objects here must be equal to 0, where we have a charge density, which is the 0 component of a current, and the 3-vector current. So the symmetry of the Lagrangian under the global U1 transformation results in the conservation of the electromagnetic current. Furthermore, since the 0 component of the electromagnetic current is just rho, so the charge density, it follows that also the charge is conserved. Okay. Nothing more than what is given by the Noether theorem. Now, let's now try to complicate our lives. So the phase alpha, which is the parameter of transformation, has no physical meaning and can be chosen arbitrarily. So its value is then constant, and once you fix it, the value is specified for all space-time points. What does it mean? This means that since we are dealing with a global transformation, this parameter alpha does not depend on the space-time coordinate. So once you fix it, it is the same everywhere in space-time, okay, at any space-time coordinate. And this is why this kind of transformation are called the global transformation. Okay. Now, an invariance for a global transformation is clearly not the most general invariance. Okay. A more general invariance is obtained for local transformations, where now the parameter or the set of parameters of transformation depend explicitly on the space-time coordinates. Okay, so in local transformation, we don't have alpha anymore, which is just a fixed real number, but we have now a function of the space-time coordinates. Okay, and this makes a lot of difference, as we will see. Let's now, for instance, consider the local U1 transformation. Okay, so the shape of the transformation is the same, but now the parameter of the transformation depends explicitly on the space-time coordinates. Okay? Mi state seguendo, ragazzi? And let's now find the expression of the Lagrangian density that is symmetric for this local transformation, which are also called the gauge transformation. Okay, so the local transformation are also called gauge transformation. So let's move back to the blackboard. Questo è molto pure.
So the local transformations in general are called gauge transformations, or just the U1 local transformation?
No, this is general.
Okay.
Also, SU3 color is a gauge transformation. SU2 weak isospin is a gauge transformation. This is general. And now, you try to understand that gauge transformation is somehow related to the gauge bosons, okay, that we introduced in the beginning. Now, allora, cambiamo pennarello. So let me start again from the for the Lagrangian for Dirac particles of Fitzgerald. Sidebar. Now, our field, transformed field, is e to I alpha of x psi. Okay?
I suddenly have a problem with the video. I don't know, it seems all blurred to me. Is it just me?
Ragazzi da casa riuscite a vedere o c'è un problema generale?
È un po' sgranato adesso, prof.
Si vede sgranato?
Cioè non si legge adesso da casa, almeno io.
Non si... io non ho che farci, ragazzi. Posso provare a scrivere un po' più grande?
No, provi a fare così. Metti la mano davanti alla fotocamera, così si focalizza sulla tua mano, e poi la toglia, così rifocalizza.
Any better?
Still the same for me. Maybe it's my connection. I'll try to disconnect and reconnect.
No, I think it's not your connection. It's a general problem here, apparently.
E ieri andava fuori poco spesso.
So apparently the same problem was yesterday, and the camera goes out of focus sometimes.
Ma dopo un paio di minuti si inizia a
Anche se c'era una nuvoletta che devo scrivere, come mai non c'è anche ora?
Non ho capito, sarà ieri?
No, dal primo semestre, tutto il primo semestre, c'era questa nuvoletta grafica su tutte.
Si può richiedere a Gambetti.
Era molto comodo, anche perché la voce si sente meglio da casa. Uno sta sulla scrivania.
Lo so.
Maybe if you try to do like a couple of lines so that it gets the focus on the board, because I think that's what it is.
Let me see if I can just... let me try to, okay, trivially switch it off and on.
It's... Yeah.
Any better?
Yeah, that does it for me.
Yeah, thank you.
Yes, I saw the system. Okay. So, now, the transformed adjoint spinor, this is psi e to minus psi alpha of x. And now we need also the derivative, the psi prime, this is, sorry, the move, e to I alpha of x psi. Now I'm using an upper index, if you see. The matter of taste. Okay, let's now make this derivative here. Now, the question is that different from before, we have x dependence also on the exponential. So this is the derivative of a product of two functions. So this is I e to I alpha of x times the derivative of alpha x times psi plus e to I alpha x times the derivative of psi. Let me write a bit more in a bit more useful way. So this is 31st, e alpha x the move psi, and then with the second term plus I e to I alpha of x, and then we have psi and the move alpha of x. I just changed the order, but nothing changed here. So what we can say now is the derivative transforming the same way as the field? Not anymore, right? Would be the case if we would have only this term here, but we also have this additional term where with the derivative of the parameter of the transformation. And this makes a lot of difference, as we will see. So again, let's now do our exercise. So L prime, I, C dot prime, gamma move, the move psi prime minus m psi bar prime to the prime. Let's substitute again everything inside. So this is I psi bar e to minus I alpha of x gamma mu. Then we have the derivative, which is given by these two contributions, e to I alpha x then psi plus I e to I alpha x psi then alpha of x. And then we have the two mass terms, the mass term, sorry. So this is minus m psi bar e to minus I alpha of x and e to I alpha of x psi. Okay, now we take these two cross products here. So this is equal to I psi bar e to minus I alpha of x gamma mu e to I alpha of x the mu psi minus andiamo più giù, se non sbattere qui. I psi bar e to minus I alpha of x gamma mu e to I alpha of x the mu psi minus psi bar e to minus I alpha of x then mu e to I alpha of x psi then mu of alpha of x, and then we have minus m psi bar e to minus I alpha of x e to I alpha of x psi. Now, this guy, as you know, is equal to 1. Let's also combine the other two. So we continue here. So this is I psi bar e minus I alpha of x e y alpha of x. Then we have gamma mu, the mu, psi minus psi bar e minus I alpha of x e I alpha of x, gamma mu, the mu alpha of x minus m psi bar psi. Come dici?
C'è una psi che nel secondo termine.
Ci guardo. Allora, sì, guardo la mano. Grazie. Okay. Now, again, this is 1. This is 1. So we're left with L equal to I, psi bar, gamma mu, the mu, psi, minus m, psi bar psi, minus psi bar, gamma mu, psi, the mu, alpha of x. Sorry, this is L. And now here you recognize the untransformed Lagrangian. And now we have an additional term here. So what we did, when the transformation was global, our Lagrangian density was symmetric. Okay, we obtained back the original Lagrangian. But now, when the transformation is local, so when the parameter transformation depends on the space-time coordinates, the derivative of the field does not transform in the same way as the field itself, and as a consequence, the Lagrangian is not symmetric anymore, because we get an extra term here, which depends on the derivative of our space-time dependent transformation parameters. Siete ragazzi? So we are in trouble, okay? So our beautiful gauge theory does not work because the Lagrangian is not symmetric. And indeed, it does not work in the way I write it here. And we need to transform our original Lagrangian, okay, in such a way to obtain another additional term opposite to this one that will cancel this one. Okay? So let's see how this can be done. Dai, lo vediamo dopo. C'è una pausa? Okay, let's make a break and we continue 12 at 20. 20 past 12.
We are doing now the transformation just to have the invariance of the Lagrangian. Noi vogliamo adesso trasformare per fare in modo che la Lagrangiana
Sì, la Lagrangiana così com'è non è gauge invariante. Dobbiamo renderla gauge invariante.
Scusi, prof.
Sì.
Quello che faremo adesso è quello che viene chiamato il gauge fixing, quindi facciamo, cioè, la scelta di gauge, vabbè, che è una ripetizione, per far sì che la Lagrangiana sia invariante rispetto a questa tipologia di trasformazione, no?
Sì, non è esattamente una scelta di gauge. Quello che faremo, se non volete andare in pausa, lo facciamo adesso, se andiamo in pausa, è di ridefinire completamente il concetto di derivata. E lo definiamo in modo tale proprio da ottenere una cancellazione di questo termine alla fine. Lo vediamo tra 5 minuti, dai. Ok?
Ok, va bene.
Vediamo 12 e 13 minuti, 12 e 20.
C'è una volta cioè all'inizio devi guardare sempre Perché non puoi scrivere libero, cioè col libero che lo scrivere le tue robe, avevo già comprato dopo la laurea c'è anche prima dopo la laurea.
Abbiamo preso il caffè e non proprio
Ciao,
per forza. Ho comprato uno.
Oggi come ieri non so se crescere a casa.
Io dico quel passo.
Io non mi dico sempre, mi devo situazione. Pensavo che era la terza, così 1000 volte. Perché tu sei tutto dal caso.
Io so,
Dopo la ricerca da me,
poi non so se scopre perché io si trova sempre pure la paura
perché più
e poi le 4
penso che sia una buona cosa. Però se di
solito metà secoli. C'erano tutti, guarda, questa cosa no, del tablet, ce l'avete se vuoi. Allora non dovrei per scrivere sul computer. E tu no? Ah, la tua è a parte? No, la mia è questa. Ah, la tua? Ah, sì.
A me tipo una volta grafica.
Ah, quindi da quello non fai delle slide?
Sì, cioè ce le ho le applicate. E più o meno. Dovrebbe qua la slide.
Bellissimo. Ancora con...
Ma non si stare o puoi anche
No, perché proprio solo per prendere appunti e tutto, però si può comunicare con il telefono e con il computer, quindi ho tutti facili automaticamente
e poi modificare avevo fatto i vaccini l'anno scorso, perché ci dava via che non l'ho letta mai. Dopo l'esame l'ho letta, certo problemi con non so, per mangiarmi il computer. Era pure così il come si chiama la mattina che lì poi diventa come la domanda, perché tipo a me ha chiesto 5 volte la domanda sulla testa. Qual è? 5 volte qual è? Qual è? Io sto dicendo la figlia di mio zio che ha 85 anni, la domanda era ancora meglio. Oh, guarda, è una spiaggia. Cioè, la prima domanda di questa era come si calcola la possibilità sulla e io gli ho detto dalla quantità di radiofarmaco concentrata in quella zona che poi si rileva con le scala di giorni, rosso, sì, qual è? Qual è la differenza di contatto? E io non sapevo dare il numero, se dargli non lo so. No, per fosse un po' internato solo so se questa domanda e poi
Ok, iniziamo un po' prima. Ok, possiamo iniziare? Siete tutti? Sono 18, ma dai, sai che possiamo... Allora... Ok, vedete la slide a casa?
Sì, prof.
Ok. Okay. So what we found in the blackboard is that the term that includes the derivative of the parameter of the transformation breaks the invariance of the Lagrangian under this infinitesimal local transformation. Okay. So in order to recover the invariance of the Lagrangian density under local gauge transformation, we must modify the derivative in such a way that the derivative of the field transforms again as the field, as it was for the case of global transformation, if you remember. So the way to transform the derivative is to replace the standard derivative with a new object, which we call the covariant derivative, capital D, okay, which includes the original derivative, of course, plus an additional term, where this A mu is a vector field, which must transform in such a way that the unwanted term containing the derivative of alpha cancel at the end. So this is the way this alpha, this A mu vector field must transform in order that we can recover the full gauge invariance of our Lagrangian density. So let's see this again on the blackboard. So again, we start from our Lagrangian, but now where the derivative has been replaced by the covariant derivative. Okay, and see what happened. So as a first thing, let me show you that with this change, now the derivative transform like the field. So for the field goes like e to I alpha x psi. Now, let's work out the covariant derivative of the transformed field. So this is the mu minus I e a mu of psi prime. That is the mu psi prime minus e I e a prime psi prime. Let me put the prime here because we have to take the product transformation. So let's substitute. This is the mu, and then we have e to I alpha of x psi. Let me go here. And then space. So this is the mu of e to I alpha of x psi, this first term, and then we have minus I e. Now we transform properly our vector field in the way I showed in the slide. So this is the mu plus 1 over e, the mu alpha of x, and then we have psi prime, so e to I alpha of x psi. Okay, let's make some trivial passages. So this is e to I alpha of x, the mu, I'm taking on this term here, the mu alpha of x psi. No, sorry. I'm just doing the derivative here. Again, we have the derivative of a product of the functions. So there is the first and the second, and vice versa. So and then we have the first not derivative and the derivative of the second side. So all these is the first term here. Okay. Now we have a term, so it's minus I e mu e to I alpha of x psi minus I the mu alpha of x e to I alpha of x. Let's collect the exponential on top of everything. So we have I the mu alpha of x psi nella derivata dell'esponente. Then we have plus the mu psi minus I e a mu psi minus I the mu alpha of x psi. Now the magic appears. So these two go away, which is the bad term, the one with the derivative of alpha. And so we are left with e to I alpha of x, the mu minus e and mu psi. That is exactly e to I alpha of x, covariant derivative of psi. And now the derivative transforms again exactly as the field does. Okay. So you can already guess that when we will now calculate and transform the Lagrangian density, this will be now symmetric for this Doppler transformation. Let's do so. Posso cancellare? Siete tutti? Da casa? Can I clear the board?
Yes.
Yes.
Okay. So our L prime, as usual, is I sub bar, gamma mu, then psi prime, and psi bar prime, psi prime. This is I, psi bar e2 minus I alpha of x, gamma mu, and we have here, this is with the covariant derivative now, of course. Okay. So this is the mu minus e I prime mu acting on e alpha of x psi, and then we have the master. Now, you will continue as an exercise. It will take 5 minutes of bare algebra, okay? And after this, you will find that you get I psi bar gamma mu, the mu minus e mu psi minus m psi bar psi, which is I psi bar gamma mu covariant derivative minus m psi bar psi, which is indeed our untransformed Lagrangian. Okay. So let me now summarize all these results on the slides. So the invariance of the free Lagrangian density for local U1 transformations, let me stress local, was achieved by substituting the standard derivative with the covariant derivative. Of course, we had to pay a price for this. And the price we paid was the introduction of a new object. We had to introduce this vector field AMU, which we call the gauge field, okay, which couples through the electron field through this interaction term. So let me again write down the Lagrangian density with the covariant derivative. When you make the covariant derivative explicit and you take now the product, you end up with the standard Lagrangian, L0, plus an interaction term, which mixes the electron field and this gauge field, AMU. Okay? And this is symmetric under gauge transformation. So by simply requiring the local phase invariance, so the gauge invariance of the free fermion Lagrangian, we are now led to an interacting field theory. Okay, our fermion field or electron field are now interacting with something. And the form of this interaction is described by the mixed term, this guy here. Okay, and this general principle is known as the gauge principle. So let me give you the gauge principle in full glory. which is at the basis of the standard model and of all essentially quantum field theories. So let psi be a physical system whose dynamics is described by a Lagrangian density L, which is invariant under global symmetry G. Now, by promoting this symmetry G from global to local, the originally free theory transforms into an interacting theory. The procedure in order to get the theory invariant under local transformation requires the introduction of new vector boson fields, the so-called gauge fields, that interact with the field psi in a gauge invariant manner, or in other words, in such a way to preserve the symmetry of the Lagrangian under this local transformation. Okay. The number of gauge fields and the particular form of the corresponding interaction terms depend on the features of the symmetry group G. In particular, the number of associated gauge boson fields is equal to the number of generators of the symmetry group G. Okay, so this is the gauge principle, which is at the basis of all quantum field theories, essentially. Okay. Now, the description of the three fundamental interactions, so electromagnetic, strong, and weak, is based on the gauge principle, indeed. So, on the invariance of the Lagrangian density under transformation that rotate the basic internal degrees of freedom, but such that the rotation angles depend on the space-time point, so they are local. Or in other words, such that the parameter of transformation depends explicitly on the space-time coordinate. They are different in different space-time points. Okay? So gauge invariance is a fundamental requirement for all renormalizable quantum field theory, QED, QCD, electroweak. The meaning of renormalizable you will understand better next week. Okay? It is a crucial requirement for all physical quantum field theories. Okay? And all these theories are known as gauge theories. So, in quantum field theory, all the fundamental interactions are described in terms of exchange of a specific gauge boson, as you know. So, for the strong interaction, we have the gluon, actually the gluons, which are spin-1 objects, so they are vector bosons and zero mass. For the electromagnetism, we have the photon, again, spin-1 and zero mass. For the weak, we have the W and the Z, again, spin-1, but now they are very heavy, order of 100 GeV. And for gravity, which is not included in the standard model, okay, we're supposed to have the graviton, which is not detected yet, okay, just an hypothesis, which should be a tensor gauge boson, so we should come with spin 2 and zero mass. Now let me point your attention to the strength of these forces, okay? So if we put the strong force equal to 1, then the electromagnetism is order of 100 or 1000 of the strong interaction, depends on the scale, of course. The weak interaction strength is order 10 to the minus 8, but then the gravity, you see here, is 10 to the minus 37. This is why it is completely negligible at the subatomic level, totally, okay? Now, the gauge transformation of QED that we will study starting from today, okay, the next 20 minutes, are based on the unitary group U1, which is the simplest. QCD and electroweak theories are based on more complex gauge transformations, which are respectively described by unitary group SU3 color, C stands by color, and SU2 left times U1 hypercharge. This will be studied at the proper time, of course, okay? And overall, the standard model is based on the symmetry under the group of gauge transformation SU2 left times U1 hypercharge times SU3 color, okay, which includes strong interaction and electroweak interaction. We will study this at the proper time. So I think this slide closes the second module of the course. So our, let's say, theoretical framework. Okay, now we have all the ingredients and we can start to construct the gauge theories and standard model using what we learned so far. Okay, so let me go on. Let me just start today the quantum electrodynamics, and we will continue and complete next week. So, a complete description of all classical phenomena related to electricity, magnetism, and optics, as you know, is provided by the Maxwell's equation, together with the equation describing the motion of a particle in electric charge and in a magnetic field. That is the Lorentz force. Okay, so this set of 5 equations essentially provides you all the information you need to describe any electromagnetic phenomena. in the unified Maxwell theory of electromagnetism, all these different phenomena, so optics, magnetic field, electric field, whatever, they are all manifestations of the same phenomenon, which is the electromagnetic field, as you all know. And the success of this theory is due to the fact that the potential that describes the interaction among charged particles is exactly known. This is, of course, not the case for the QCD. QCD is much more complicated. Now, the classical theory of electromagnetism was easily adapted to the quantum mechanical formalism, and so derived successfully describing electromagnetic phenomena at atomic and subatomic scales. And this you know perfectly. Already, just the atom, you need to have electromagnetic phenomena at that level. And it was also adapted to the special relativity, which is our case. Of course, we want to build up a relativistic quantum mechanical theory. And in fact, one can derive the Maxwell equation in the covariant form. Questi rettangolini sono sballati tutti. Vabbè, fuori sistema. In this way, so the two non-homogeneous Maxwell equation in the covariant form become this way, okay, in this very compact notation, and the two homogeneous one become can be written this way, where this F mu nu is the electromagnetic field strength tensor, which is given in terms of the components of the electric field and the magnetic field. I think you know this already. And this J nu that appears here, okay, is the 4-vector electromagnetic current, okay, essentially the one that we already saw last time. And this epsilon alpha beta gamma delta is the Levi-Civita symbol, which is a fully antisymmetric unit tensor of rank 4. So it is equal to 1 if the combination of these indices is an even permutation of 0, 1, 2, 3. It is -1 if it is an odd permutation. It is 0 otherwise. Now, from the historical point of view, a quantum relativistic theory of electromagnetic interaction was developed in the framework of the perturbation theory, okay, by Tomonaga, Schwinger, and Feynman in the 40s and 50s of the last century, and they all three get the Nobel Prize for this in 1965. Okay. Of course, this is today an historical perspective. Now, the next evolution was to encode electromagnetism in the language of the quantum field theory, leading to the theory of the quantum electrodynamics, or QED, where charged fermions fields interact through the exchange of virtual photons, which are the gauge bosons of the electromagnetic interaction. Okay. Now, at fundamental level, electromagnetic interaction occur among all charged leptons, so electrons, muons, and tau leptons, and their antiparticles, of course, and all quarks, because they are all carrying some electric charge, okay, and all their antiparticles as well. All charged leptons have the same charge, which is a charge of the electron, which you see here in terms of Coulomb, so it's extremely small charge, of course, and the quarks have a fraction of the electron charge, okay, either +2/3 or -1/3. So since all of them carry electric charge, all of them must interact through electromagnetic interaction, and not only, as you know. The only elementary fermion which is not involved in electromagnetic processes is the neutrino, because neutrino is a neutral particle, does not carry any electric charge, and so it doesn't carry any color charge as well, so it can only interact through the weak interaction. Now, let's get back to what we learned today. So by simply imposing the invariance of the free Dirac Lagrangian density under local U1 transformation, or if you like, gauge U1 transformation, and substituting the standard derivative with the covariant derivative, we obtain an interacting Lagrangian. Okay, so we had the let's say the free Lagrangian term here plus an interaction term, which is a mixed term in the fermion field and this vector boson field. Okay, with a mu is the gauge field that couples the two fermion fields of charge E. Now, in order to obtain the full Lagrangian of QED, we just need to add one more piece, which is the kinetic term of the gauge field. Okay, so we have the kinetic term and the mass term of the fermion. We have the interaction term already between fermion and field. What we miss is the kinetic term of the field, the gauge field. Now, we will not derive this, but it can be shown that this kinetic term is given by -1/4 F mu nu, where F mu nu is the usual electromagnetic field strength tensor that I showed before, which can be written, okay, in terms of the AMU field in this way. This you can derive easily on a few passages, okay? Where, of course, our vector boson needs to transform in the proper way in order to preserve the gauge invariance of the Lagrangian density, okay? So once you do so, you add this term, you have now the full expression of the Lagrangian density of QED, okay? So we have the kinetic term of the fermions, the mass term of the fermions, the interaction between the fermions and the electromagnetic field, and the kinetic term of the gauge boson. Now you might ask, so why in this Lagrangian we do have a mass term for the fermion, but we don't have a mass term for the gauge boson? And the reason is that if you put by hand a mass term for your gauge boson here, you will immediately break the gauge invariance of this Lagrangian density. So if you put a mass term for AMU, the Lagrangian will not be any more symmetric under the gauge transformation. And so it is natural to associate the gauge field AMU to the massless photon field, of course. Okay. So this mixed term here is essentially the interaction between two fermions through the exchange of a virtual photon field. If you now substitute this Lagrangian density into the Euler-Lagrangian equation, as we did for the free fermion case, what you obtain is now the Dirac equation for a charged particle in the electromagnetic field. Okay, so you're going to have this additional term in your Dirac equation, which tells you that it is now an interacting fermion, not anymore a free fermion. So how can we connect now this Lagrangian with the Maxwell equation? So the connection becomes more apparent by writing the Lagrangian in terms of the four-vector current Jmu, which is minus E psi bar gamma mu psi, as we learned. Okay, so you put now Jmu here rather than all these objects here, and by putting this into the Lagrangian equation for the photon field AMU. Okay, and with the attention to express your electromagnetic field strengths on F mu nu in terms of the photon field as well, in the way I showed before, this way. So once you put everything together and you solve this Euler-Lagrangian equation for the photon field, you get back to the Maxwell equation in the covariant form. So everything is consistent, okay? There are just two different languages. So the theory of electromagnetism, so essentially the Maxwell equation, can be derived by simply requiring a local U1 gauge transformation, a gauge symmetry, yes, to the Lagrangian for a free particle satisfying the Dirac equation. And I think we can already stop here. Okay. So by applying the gauge principle and the simplest U1 gauge transformation, we derive the expression of the Lagrangian of QED. Okay, which includes all the QED phenomena. And then we will start next week to develop the perturbation approach of QED, the Feynman diagrams, the Feynman rules, how to draw a QED reaction, how to calculate its cross-section using the Fermi-Golden rule. Okay? Any questions? Okay. If not, I'll see you next Wednesday, hopefully in presence. We don't know how the situation evolves here. Let me, for the moment, stop the registration.